Thank you so much, Pink, for the nice introduction. So today I'll be talking about introduction to transfer learning, and I'm really honored to be invited to give this talk. Although I feel I'm not so qualified, but I'll try to do justice to the invitation. A little bit more about myself. I'm a second year master's in computer science student at Texas A&M University. I'm advised by Professor Atlas Wang, and my research in I'm interested in deep learning and computer vision, and my focus is essentially object detection, emotion detection, and image reconstruction and image-to-image translation. And for my most recent project, I worked on building an energy-efficient deep learning OCR system to detect and recognize the text appearing in videos. And our team won the second prize in the CVPR challenge. So uh, today I'll be talking about transfer learning, and I'll try to give a brief overview of what give the basics of transfer learning, and tell a little bit more about when you should use transfer learning, how you should use it, and like how the features are transferable, which would give an intuition where like whenever you're using transfer learning for practice. So the my outline for the talk is essentially for starting with giving the motivation, followed by uh, telling about the concepts and the notations that are involved in transfer learning. So that once you're familiar with these basic notations, when you read further research papers, it will be really helpful for that. Followed by telling about these 2 points will be very helpful. That is explaining about when and how to use transfer learning and how transferable the learning features are. So with this, you would have the intuition and a nice knowledge about uh, where how to use transfer learning, what kind of data set needs to be used, and things like how many layers need to be trained to get good performance. So this would provide that intuition. Followed by that, I'll tell about the applications of transfer learning, and then we'll have a PyTorch demo, and then followed by Q&A. But please feel free to interrupt me if you have any questions during the talk, and I'll try to answer the questions as far to my best ability. Okay, so motivation for transfer learning. I'm sure that all of you have by now been playing around with deep learning, some image classification tasks, and so on. So for all these tutorials or the projects that you're working on, transfer learning, you might have been using transfer learning. Maybe you know it or you don't know it, because uh, for deep neural networks, they require a large amount of data set, and with to be able to allow them to perform that well, it's important that these deep neural networks are provided with a large data set. Uh, but having that scale of data set is not always possible. So when you have a smaller data set, you used a kind of transfer learning to allow the model to train for your specific task and have good performance. So this is it's been a myth that is deep neural networks require a large amount of data set, and transfer learning like allows to train the models with a small amount of data, and even then perform really well. So this is one of the reasons why transfer learning is widely used, and it has been said by the pioneer of deep learning, that is Andrew Ng, that it's going to be the next driver of ML commercial success. And some other aspects why transfer learning is used is that it's used to reduce the overfitting for your data set. Whenever so the deep learning models, they have a large number of parameters, but when you have a small data set, the models can tend to overfit on the particular data set. So to avoid that, transfer learning is used. And another aspect why transfer learning is used is to boost the generalization performance. So what happens is whenever the deep learning model is trained on a particular data set, even though the data set might be big, the model tends to overfit, tends to overfit on that particular data set. So when a particular model is trained on one data set and then trained on the next data set, then it tends to remember some of the features, some of the training data that it saw in the previous one, and that enables it to be able to generalize better. So, so now let me talk about the concepts and the notations that are involved. Before I jump into the notations, I'll just give a little bit of probability 101. That is, first two things, that is marginal probability distribution and conditional probability distribution. Marginal probability distribution is essentially probability of a particular variable independent of other variables, and conditional probability distribution is probability distribution of a particular variable where dependent on another variable. So given a particular so for transfer learning, there is always a domain and a task. So domain especially has a feature space and a data distribution. So feature space is essentially, let's say we are trying to, let's take an example of image classification. We want to train a model to be able to, given an image, classify whether it's a dog or a cat. So over here in the domain here, X would be, if our data set has a number of dog images and cat images, the feature space would be essentially the images of the data set. And so one particular image which consists of the number of pixels would be one row, and that would be a particular image. And the probability distribution, that is a data distribution, that is images of cats and dog, would be P of X. And the second thing is task T. So this is, you have a label space Y, which is in our case, it would be either it's a cat or a dog. And the second is the objective predictive function, that is the target conditional probability that the model is trying to learn when it's training with a given input data and the class labels. So whenever we have the task, like the example which I gave, that is you have an image and you want to try to have a mapping between the image and whether it's a cat or a dog. So this conditional probability distribution, what it does, so when you train the model, it learns this conditional probability distribution. So now, given a source domain, now that we know what is a domain and a task, so for a given source domain and a learning task, and a given target domain and a target task, transfer learning is essentially the process of finding the target conditional probability distribution with the knowledge of the training that is done for the source, between the source domain and the target, that is the task of source task, DS and DT. Given that DS is not equal to DT and TS is not equal to DT. So with this notations, there are 4 different scenarios in which transfer learning can be categorized into. That is, when the feature space of the source domain and target domain are not the same. That is, the number of features that are there, the number is different. So one of the examples for this is cross-lingual adaptation. That is, you are training the source domain is training the model for English language, and then the target domain is to be able to, the model should be able to perform well for maybe French. So the next is when the conditional probability distribution for the target, for the data, that is the data distribution, is different between the source and the target. This is the case of domain adaptation. That is, when the source domain and the target domain are different, then transfer learning is so that comes under domain adaptation. The third case is when the label space is different for the source domain and the target domain. And this occurs together with the last case, that is when the target conditional probability distribution is different from the source probability target source conditional probability distribution. And to tackle this, this is essentially happens when the whenever for this case, what is generally used is oversampling, undersampling, or SMOT to tackle the cases. So when and how to use transfer learning. Whenever we have a data set, this is a good and this shows a good summary of how to find, like, when and how to use the transfer learning. That is, whenever we have a source domain, whenever the target task that we have, the data set. So here, this the small data set and the large data set means the target data set. And when the target data set is essentially has a similar distribution to the source data set, and when the target data set is small, then it is better to use a linear classifier or maybe train the last one or two layers for training the deep learning model. This is because when we have a small data set, the model can tend to overfit, and because of that, it's better to train only the last few layers. And when we have a larger data set and the data set is similar, in that case, it's advisable to train more number of layers or even the entire layer. But if you take copy the source domain weights and then fine tune the entire network, it can result in a higher performance. And so when you have a small data set and when the data set distribution is different from the source, so when the data set target data set is small and when the target data set probability distribution is different from the source probability distribution, in that case, we cannot use a linear classifier on top layer as mentioned in the first box. This is because in that case, what happens is the later layers, they are more specific to the particular data set, whereas in the earlier layers, they have features that are general. So it's suggested that you can use linear classifier on the earlier layers. And lastly, when there is a large data set and when the data set probability distribution is different, in that case, because the model is again it's been trained on a different distribution, it's better to train the entire network, or it's better to train all the layers. And if the weights are copied, that is from the source domain, even in that case, the model can tend to can get a little bit of generalization power from the previous model. That is, I can just clarify this. That is, the model is first trained on the source dataset and then fine-tune all the layers on the target dataset. So before I move to the next slide, anyone has any questions, please feel free to unmute yourself and ask. Oh, I'm really sorry. This is not the 4 categories of transfer learning. This is essentially like, first of all, the model is trained on the source dataset, and you have that particular model with you. So for your current dataset, how to use transfer learning, that is what this means. So if your dataset has similar probability distribution to the model, to the training data that the model was trained on, and if the data set is small, then you use a linear classifier. Or if your data set has similar probability distribution to the training data the model was trained on, and the data set is large, then you train the model for more number of layers. But if your data set is small and if your data set probability distribution is different, from the training data of the model, then you will be you are in trouble, and you have to see how to use maybe a linear classifier on the earlier layers, because in that case the earlier layers have general features which could be applicable to your data set as well. But if you use a linear classifier on the later layers, then it not be possible, because the model is because those features are more specific to the source domain data set. Yeah. Does that clarify the question? Okay. So yeah, I think I have not explained quite well, but feel free to ask your questions, and maybe I can give better answers and try to clarify. Okay. So the next is how transferable are the deep learning features? This is so first let me so this is the graph which I'll be explaining, but before that let me first explain you what is the training settings that has been used for this. So over here there are 4 training configurations. The first one is, so before that, this rectangle means weight of a particular layer. The ellipsoid means the activations for a particular layer. And dataset A, dataset B is there are 2 datasets, and it's essentially half of the ImageNet. Dataset A is first half, and the dataset B is second half, and the model is an image classification network. So the first one which you can see on the top is essentially that is base A network. That is, the model is trained on the dataset A. The second one is model trained on dataset B. The third one is that is first n layers. In this case, 3 is the number of layers. The weights are copied from base B network, and then the network is trained on the dataset. So there are 2 cases. That is, when these n layers are frozen and the 8 minus n layers are trained on the dataset B. And the second case is when the entire network is trained on the dataset B. So that is B3B and B3B plus. Lastly, there is the model. The first n layers are copied from base A network, and then the model is trained on the dataset B. So this is where we are trying to find what kind of transfer learning settings works best. And over here, the first n layers, so here A3B is again, the first n layers are frozen, and A3B plus is when the first all the layers are trained together. Okay, so in this graph, first of all, you can see the white dots. That is the base B network. That is the second one. The deep learning network is trained entirely on the dataset B. And cell for B and B plus is the third one. So you can see here that the model performance for the first 2 layers is similar, almost same as the base B network, and then as n increases, the performance drops, and then it comes back again. It comes back to actual performance. So this performance drop is the reason for this is because of fragile co-adaptation features. So if you see here, for n is equal to 3, 4, 5, in that case, what happens is whenever these deep learning networks are trained with the help of backpropagation, the 2 adjacent layers learn features by interacting with each other, and this is not possible when you freeze the weights. That is, if n is equal to 3 and these 3 layers are frozen, and after if we are just training from layer 4 till the end, in that case the interaction between layers 3 and 4 is not possible, And this is what is the co-adaptation features. That is, both the layer features interact with each other and learn for optimal solution, which does not occur when you freeze three layers. So as the number of n increases for the n from n is equal to 3 to n is equal to 6, the performance drop because of this reason. And as n further increases to 6 and 7, in that case the performance comes back, and in what happens there is backpropagation is able to relearn these features. So this is the case for B and B. The next one is B and B plus. As you can see here, that is the blue circle with a plus sign. For this, you can see the performance is almost same as the original network. So this is as expected. There is no performance drop because the entire model is allowed to be trained, and the co-adaptation features occurs, and the network is being trained and gets the same performance. The next one is transfer A and B. Okay. That is red diamond shapes. Here you can see that the performance keeps decreasing as n increases. So this is because of two reasons. The first one is fragile co-adaptation features, and the second one is because as the layers go deeper and deeper, the features that are learned are more specific to the dataset. The initial layers features are generic, and as the layers go deeper and deeper, the features become more specific to the dataset. So if you see here, the layers n is equal to 3 to 5, the performance drop is attributed due to fragile co-adaptation features, and for layers 6 and 7, the performance drop is due to the second reason, that is the features are more specific to the source domain. So because you can see, if you freeze the 6 layers with dataset A and then just train the last few layers, last 1 or 2 layers for the target domain, then what happens is if the if dataset A was different from dataset B, then the features that are there at layer 6 would be not be suitable for dataset B, and hence the performance like there is a sharp drop in the performance. And last one you can see is that A and B plus, that is the features are copied from the base A, and the entire model is allowed to be trained. Over here you can see the performance increases regardless of n is equal to 1 to 7. This is this shows that when the model has been trained on another dataset, and it's trained on A dataset, and it's then trained on B dataset, the whatever it learned in the previous one is still present, and hence it's able to generalize better, and which improves boosts the performance. So that's the reason for this. So that's why you might have seen in the tutorials that whenever there is a transfer learning that's taking place, like for example, there is a pre-trained model that's trained on ImageNet, and then there is you have a particular your data set, and you just train the one or last 2 layers for training the model. In that case, the data set that you use would be similar to ImageNet, and so it is the case where it's a case when the features are the last few layers features will be helpful for your target data set, and it will give good performance. But if your data set is different, then there will be a performance drop. Yes. So anyone has any questions? Okay. So if there are no questions, I can go to the next one. That is for now. Let's see the applications of transfer learning. Like, as I said in the earlier, that transfer learning is widely used is used almost in many places. And some of the reasons why it's used are, like, for example, it's one example is learning from simulation. So if you take the example of self-driving cars, wherein it's time-consuming, expensive, and even risky to collect real-world data. So in that case, to allow the models to learn faster, the simulations are used. And simulation is very important for large-scale machine learning projects. And one thing that what needs to be taken care is that the simulation data is as close as possible to the real world data, so that the model can generalize to its target tasks well. The second one is that is domain adaptation. So for example, you can see here there is real images and cartoon images. So if the task is to be able to classify apples and pears, and the number of real world apple pear labeled dataset is less, in that case, and the cartoon images, there is a lot of cartoon images labeled images present. So in that case, it's better to use transfer learning, that is train the model on cartoon images, and then later on have fine tune the model with the real world images, and then it can perform good. Instead of training the model on the small data set, that is real images, it might overfit and it might not be able to generalize well. And then there is an example of transferring knowledge across languages. That is, whenever these language models require a huge corpus of data set, and for English, it's for widely spoken languages like English, it's fine, but for the languages where these data sets are not available, the knowledge that's learned in English, or the grammar, the syntax, these can be transferred to other languages where the dataset size is small. And lastly, some computer vision applications also use transfer learning. For example, when these ImageNet image classification models such as ResNet, InceptionNet, and MobileNet, etc., they are used as a feature extractor, and these are fixed and they are not trained. But then the rest and are used for tasks such as detection, segmentation, image classification, and etc. So transfer learning is very important, and it's used in it's widely used. And so yeah, I think does anyone has any other questions? I think that's all I have to present for transfer learning. Okay, so if there are no more questions, I think I hope I have given a rough overview of the given explanation of transfer learning. And told about how do you know which exact features are being transferred. So okay, this is essentially in a deep neural network. The initial few layers learn the general features, which would be applicable to many tasks. But as the layers progress, the features get more and more specific to the data set. So, for example, in ImageNet, there are large number of breeds of dogs. So the the initial few layers, they'll be focusing on the edges and things like that, the horizontal, vertical edges. But as the layers progress, the features get more complex and complex. And since in ImageNet there is a large amount of breeds of dogs, so in the later layers, what happens is uh, mm, the representation power of the deep neural networks focuses more on trying to get the features for the different kind of breed of dogs. So it depends mostly on the data set that's being used. Does that answer the question? And actually, you can actually try to visualize the features as well. So that is also one way to find out like which features are being learned. So that's also helpful. Any other questions? Okay. If there are no more questions, then maybe I can just summarize about just a quick summary would be this table. Would if you can take this home, then I think that is more than enough to be able to use in whatever practical situation that you come across. So the first thing is that it depends. There are two things. That is the size of the dataset and the similarity of the dataset with the uh, on the data that is the model was trained on. Based on these two parameters, you can adjust how you will be using transfer learning for your particular model. So if you take this home, then I think you will be able to do your transfer learning tasks. Okay. Lastly, I have a PyTorch tutorial. This is maybe you can if you would like, you can do it now. And if you can use, this is a Google Colab tutorial on PyTorch with PyTorch. And you can start working on it. And maybe if you have any questions regarding the tutorial, you can ask me. Or if you have any other questions regarding transfer learning or anything, you can ask. Yeah, open to questions. And before that, just I would suggest these are some resources to go through. The first one is the CS231 and transfer learning. This one, and the second is the paper. This is a NeurIPS paper in which that particular graph and it shows how transferable the features are. And this is another blog which you can see to get some more understanding of transfer learning. Yeah. Feel free to ask your questions. Sure.